Okay, so let's continue our discussion for the theta correspondence. So recall last time we have basically spent quite a lot of time to classify explain the classification of reductive dual pair, and then we have explained what is theta correspondence or what is Hall duality conjecture. Then I think I mentioned three important questions for the theta correspondence. These are basically the central questions for theta correspondence. First one is that determine when a representation occurs in theta correspondence. Second is describe the small theta. Third one is describe the big theta. Okay, so today I will going to have a deep zoom in look for this topic for basically focus on the complex group. So, right, but before that, I think last time we have mentioned that about the occurrence, so about the first question. So I think one of the most important this is a conservation relation. Okay, so this is the one of the most important formula in conservation. Okay, it tell me that. Right. Okay, very clever. Right. So I have mentioned that the typical example, I think this is one of the most important case, is that you consider the orthogonal symplectic dual pair, and you consider a representation which is a representation, irreducible representation of orthogonal group. Then you consider the first occurrence index for this representation, which is defined to be in this way, this M. So for symplectic group, actually you have only one with tower, so you just write M pi. So this is nothing but the smallest minimal n, minimal 2n, such that big theta of pi from pi goes. So this theta is a map sense OW representation to SP to M R representation. Okay. So this is actually it's really doesn't matter which field, SP to NF, where F is a local field, either R or complex number or p-adic field. So this is the minimal 2n such that the theta lift of pi to SP2NF or maybe mathematic group is non-zero. So this number plus, in general, you cannot compute it directly, but you will know that this number plus the first occurrence index for pi tensor with the sign representation of orthogonal group is equal to 2 times of dimension of pi. Okay, so this is a first occurrence conservation relation. Okay, there's other cases. For example, for the case F is a p-adic field, then so for a width tower T, you will have something called a companion width tower. So this is a width tower have a anisotropic kernel, which is V prime A, and satisfy this kind of weird condition at the first sight. It's that if you have a width tower T, so recall that the shape of width tower is something like this. so it's a collection of isometric class of epsilon Hermitian spaces, and in this class there is a smallest space which called VA. This is an isotropic space. So the space it is anisotropic. For example, if it's a skew Hermitian skew symmetric form, then so this will be a without of symplectic space. So zero space is this VA, and this is this VA at hyperbolic space. So all possible addings will contribute to this with tower. So anyway, what you need is V plus minus V prime A. So this space add together is a maximal anisotropic epsilon prime Hermitian space. So if it's it is symplectic space, so epsilon prime corresponds to a symplectic space, then it means this A and VA and V prime A are just zero space. Okay, if on the other hand, the epsilon prime is 1, then you will have Hermitian space or quadratic space. In that case, VA plus minus V prime A will be the quaternion. Okay, so in this case, the conservation relation reads that the first occurrence of pi for the with tower T plus the first occurrence for the with tower T prime added together is 2 times the dimension of okay, so 2 times of the dimension of the original space where GX on plus the dimension of maximal anisotropic space maximal dimension for the anisotropic space of type epsilon prime. So this is the maximal dimension. Dimension of an epsilon prime Hermitian space. Okay, so right. For example, in this case, the example case, so this one is just a 0, so it's 2n plus 2 times dimension w plus 0. Okay, for the also right. So I think it's good to give one more example. But let me see. So example is that when G bar W is symplectic or metaplectic. Okay, maybe I should write GW is symplectic. Then and the F is local. Then this D, A, and max is equal to 4. And the F is local, sorry, am I right? Symplectic. Okay, so I think I should write when F is p-adic. And when unfortunately for real group, you will have more with towers than you think. So you have a lot of other with towers because OPQ, for OPQ, this kind of space, so the with tower is classified by the difference of P and Q. P minus Q, classified with tower. So for for orthogonal group, you will over p-adic field, you will basically have how many with tower you will have for, okay, I forgot. Okay, so you have limited number. I think you will have 8 with towers for p-adic field, but for the real field, you will have infinitely many with towers of orthogonal group. Huh? With tower? Yeah, relevant with tower, you only have 2, but you will have all other with towers. So, right. So I think this form, it's good for the p-adic field, but for orthogonal group over the real field, it has a more complicated form. Okay, so to prove this kind of theorem, basically you will have you need to prove 2 inequalities. Basically, you prove one inequality is the first occurrence index add together is bigger than equal to this number. And another is the, okay, so this direction is actually a simpler direction. This inequality is a consequence of the trivial representation for the anisotropic tower, so something called anti-split tower, which is a tower with tower such that its anisotropic kernel is the maximal anisotropic space. So this tower is called anti-split tower. So in the anti-split tower, the trivial representation of the original group is actually occur very late. It must occur in this dimension. So this is proved by using Fourier transform kind of consideration. Okay, historically, different people for different field, different cases give a different proof. And then in Sun and Zhu's paper, they give a uniform proof of this result. Okay, so this is one of interesting point is that you prove the late occurrence of a specific representation, which is a trivial representation. And so now I'm going to explain why this equality, this inequality, actually you can prove they're equal, okay? So why this inequality implies the inequality above? So this comes down to a very important notion called a seesaw pair, and it's a very important trick. So we need a notion called a seesaw pair. Okay, so seesaw pair. What is a seesaw pair? Seesaw is just so I think all of you have played seesaw during your childhood. So it goes up and down. Okay, seesaw pair is basically a pair of reductive dual pairs. So this is pair is, so a pair of reductive dual pair G and H and M and M are 2 reductive dual pair in SP W for some big W. And it satisfies that condition that G is contained in M. Okay, as a consequence, it will imply that H is, so N is contained in H. So I'm using this diagram to denote the relation. So something below is smaller group, something above is a bigger group. So this line implies that this denotes that G and H are dual pairs and M and N are dual pairs. Okay, so this is the notion of seesaw pair. So for seesaw pair, the most important thing is called the seesaw identity. So let me copy this one here. Okay, so maybe I explain it here. So what is a seesaw identity? Basically, you take irreducible representation inside G bar, and you take irreducible representation sigma prime inside N bar. So where G bar and N bar are in the most of the case, it's just the group G and N themselves, and the only case is that it could be the mathematic to cover when the other guy is orthogonal, odd orthogonal group. Okay, in this case, we are interested in seeing that you have, if you take these two irreducible representation, then you can have sigma, then you consider its big theta. Okay, so this is a representation a priori as a representation of H. Then you are interested in restrict this representation on N because N is a subgroup of H. Then to see whether sigma prime occur in this representation. So you are interested in this space as N representation. Okay, so but this space is naturally isomorphic to Hom of, because sigma is an irreducible representation, you can write as G cross H sigma tensor theta sigma prime. Okay, sigma tensor sigma prime. Okay, so I think I should write a bar. So I think I should put bar everywhere. Okay, so this is obvious because this is Shor's lemma, right? For in our setting, which says that the Hom of sigma is just a complex number. Okay, and then you see that this, for this representation, G bar act by sigma. Okay, so therefore this is nothing but, so this is a maximal quotient. So we have shown that this is the omega divided by the intersection of all kernels of T, where T is intertwining operators from G bar to the wave representation to sigma, okay? Right? So the point is that you can replace this by omega. So this is isomorphic to Hom G bar cross H bar, the wave representation from sigma tensor sigma prime. Okay, then you are win. So because this formula is symmetric for G and G and N, right? Sorry, this is N. So you can play the same trick. So this is isomorphic to home from G bar cross N bar. But here you have theta sigma prime tensor sigma prime, sigma tensor sigma prime. So this is isomorphic to, you plane the, again, Shor's lemma. This is home G bar big theta sigma prime sigma. So this is a seesaw identity, which says that the intertwining space from the big theta sigma to sigma prime is naturally isomorphic to the intertwining space from the theta lift of sigma prime to sigma. So the situation that you have sigma prime, so you have theta sigma prime. So you can, roughly speaking, the number of times sigma occur in here is same as number of times sigma prime occur in big theta sigma. Okay, so let's continue. So this is the seesaw identity, but so from this seesaw identity, you see it's quite important in the application because you're always dealing with irreducible representations in most of the case. In the application, you want to know that the structure of big theta because you wish it to be irreducible in the most of the case. Okay, so on the other hand, let me give you an example to apply seesaw argument to deduce this inequality from the late occurrence of the trivial representation for the of the anti-split tower. So the idea is this: you consider this kind of seesaw dual pair. You have a space V, W, and V. So you consider the dual pair. Okay, so you basically double it. So the situation is that WV. So we assume that W is an epsilon Hermitian space, and V is an epsilon prime Hermitian space. So for the type 1 dual pair, so GW cross HV is a type 1 dual pair in SPW tensor V. Okay, but now we are not considering this dual pair, but we're considering a larger one. So we consider the space W, larger space W, which is W tensor V plus W tensor minus V. What is minus V? Minus V is just a V as a set, as a vector space, but the form is given by minus of the form of V. Okay, so we consider this space. So therefore you can write it as W tensor V plus minus V, right? In this case, actually, what you really do is you will think about in this situation. So Thai is a irreducible representation of GW, okay, or maybe G bar W, and the first occurrence, V is the first occurrence, is first occurrence of pi in tower T, the V prime is the first occurrence of pi in T prime. Okay, so we consider this space. Okay, so in one hand, this G bar W is actually diagonally sit in GW cross GW. So we have two dual pair. One reductive dual pair is a non-irreducible dual pair. This is this one. Okay, this GW pair with this HV and this GW pair with H minus V prime. So when you put a minus, it will give you a dual representation, actually. Okay. A conjugate representation. We also consider another dual pair, which is the diagonal subgroup of GW cross GW. And the H of V plus minus V prime. Okay, we consider this two dual pairs. So we consider sigma. Let's take sigma to be the trivial representation. And sigma prime to be the product of representations. Tensor product of small theta pi with small theta pi prime. Sorry, here's not pi prime. Theta prime. So it's a theta lift of pi to the other group. Okay. Then we consider the seesaw dual pair. So somehow we have certainly pi and pi check have a natural pairing to the trivial representation. So we have this home space. This home space is non-zero. Okay. And it implies that, so this home space is certainly, so this pi is certainly a quotient of theta. So you have theta pi, then you can lift it back, right? You have theta pi. So theta pi is also always contain pi as a quotient. Okay. So therefore, it is what should I say? Right. So it's so of course you also can consider the big theta. So the fact is that you observe that big theta of, maybe I use another color, big theta of theta pi tensor theta prime pi. Okay, it has a quotient to pi tensor pi check. Actually, so therefore, if this space is non-zero, then big theta pi tensor theta prime pi to trivial representation is non-zero. And then you apply seesaw identity. It means that the big theta lift of the trivial representation to here is the big theta trivial will have a non-zero. So this space to the theta pi tensor small theta pi prime, this space is non-zero. So this implies this space is non-zero. But this space is non-zero in particular implies that this theta lift is non-zero. Okay. So here this identity is a seesaw identity. Okay, so because here it's non-zero, so this one is non-zero, implies that this one is non-zero. Not zero. So implies that, so this implies that this big theta pi of v plus minus v prime is non-zero. Okay, as a consequence, it means that the dimension of v plus minus v prime should be bigger than equal to this one, because by assumption, this v plus minus v prime is an element in the n-T-split tower. So it's the first occurrence is given by this formula. Okay, so this is the application of the seesaw identity. Any question? Right. So yeah, so this is basically the easy part. Then the difficult part is to show that the other direction of inequality. To prove the other direction, you need some very refined knowledge of the degenerate principal series. Again, it's a structure of theta lift of trivial representation. You need very specific knowledge. Okay. Let's continue. About the let's continue about the theta pi or big theta or small theta, try to understand it. So one of the easiest case is that when G bar, so if you pi is always an irreducible representation of G bar. So when G bar is compact, then this is the easiest case, because if G bar is compact, then from the general theory of representations of the topological group, you know, the wave representation will decompose into direct sums of irreducible representations, isotypic components of pi, and okay, so first of all, let's recall that when G bar is compact, so what you know is that the set of the set of irreducible representation of G bar. Okay, so first of all the irreducible representation of G bar is are unitizable, right? These are unitary representation when G bar is compact. And then as a topological space, this is just a discrete set. Okay, you have no problem with this. And then so G bar is compact, then this wave representation can be written as direct sum. Of course, you have to do some topological completion of pi tensor big theta pi, where pi running over irreducible representation of G bar. Okay. In this case, because pi is unitary, and the wave representation itself is unitary, so as a consequence, it will imply that the big theta pi is unitary. Okay. On the other hand, big theta pi has finite length. So therefore, you know that big theta pi must be semi-simple. Finite length unitary representation of a group is semi-simple. This is because you take any irreducible submodule. It exists because of finite lengthness. You can take the orthonormal complement of this sub-representation. So these two representation will like direct sum together, give you the original representation. And the orthonormal complement is also a finite length representation, but with length -1. Then you do the induction, you see that this representation is semi-simple. And the Hall conjecture tells you that the maximal semi-simple quotient has only one component. So therefore it implies that, so this theta pi is semi-simple, which implies that. So I give the proof basically. So this implies that big theta pi is actually just a small theta pi. Okay. So unfortunately, I don't know where to find the explicit description for F is p-adic group. So there's a few cases G bar is compact, very few cases when this G is like U1 over the p-adic field, it is compact. And then the quaternion group, the orthogonal group for the quaternion form, then this group is compact. For other, so this case is, I think you should be able to find the explicit description, but the specific case is that when the field F is the field of real number or finite field, then you have complete description of the small theta and the big theta. Okay, so I think here, I think I should assume that F is local. Okay, I haven't mentioned that this one is that remark is that when F is a finite field, finite field, fine. So you should not expect big theta pi is irreducible, can be reducible. So you don't have Hall correspondence over the finite field. Okay. But you still have a complete description of the big theta pi. So hopefully I can cover this next time. But one of the case is that a quite interesting case is that when F is a real field, and so you will have something called a compact dual pair case over R. So basically you will have three possibilities. Either G is orthogonal group of a vector space, R vector space of dimension M. So you should so the orthogonal group over the for Euclidean space basically, and then H is a symplectic group, and you can have unitary group over. So this will act on Cn. This will act on Rn. So this will be again a symmetric space, isometry group of a form, but now it's a form on the quaternion. So this is a compact form of a symplectic group. So the counterpart of H will be SP2NR, UPQ, and O star 2N. Okay, so the amazing part is that the maximal compact group subgroup inside these three cases are all unitary groups, basically. Essentially are all unitary groups. So this O star 2N, I think last time I have explained, but let me explain again. So this is so O star 2N is the symmetric the group G in GL NH such that so GV GW is equal to BW, where this form I think I can write XI YI is given by summation XI. Maybe I call it J Y I bar, where J square is equal to -1 in the quaternion. So this XI YI are all quaternions. So this is right. This is the form, and you can check it is skew symmetric because XI YI bar is just a summation YI J bar XI bar. So this is J bar is minus J. So this is minus YI XI. Okay, so this is O star 2N. Okay, so again it's something called a Hermitian symmetric. Basically, what is Hermitian symmetric domain? A Hermitian symmetric case is that G mod K can be realized as a open domain inside C of some big N. Okay, so the typical case is that this one you have seen quite a lot, SL2R divided by K. This is the upper half plane. Okay, so it's a symmetric domain case. And this three group are like Hermitian symmetric type of space, because G divided by its maximal compact is a Hermitian symmetric domain. Okay, so in this case, so this group will have something called a discrete series, holomorphic discrete series, or anti-holomorphic discrete series. These are why call this number is because these discrete series representations can be realized as holomorphic functions on the holomorphic sections of vector bundles on the symmetric domain. But anyway, so these modules are fairly simple, just like you know the Verman module, right? So the GK module of this kind of holomorphic or discrete anti-holomorphic discrete series are kind of a highest weight module and the lowest weight module, depends on the way you talk about. So so the point is that if I give you a compact group G and the H is the counterpart of the compact dual pair, then the wave representation will decompose as direct sum of irreducible representation running over. Of course, it's not all occurs in general, but most of them, many of them will occur. So we have a complete description, and its theta lift is a unitary highly sway module determined by its lowest K type. So the GK module of this sigma pi so the High-Shander module, which is basically a quotient of mu tensor. So in this case, okay, I would like I forgot to say that's the complexification of. Okay, so I should write this as H. So HC will have the decomposition of K plus P plus plus P minus, and the K plus P plus is okay, maybe I write P minus is parabolic in H. So that basically the complexification of the algebra of H will have a decomposition. So therefore the minimal K type will have a K action, so it can be extended as a K plus P module. And then you tensor with the whole universal enveloping algebra of G. So this is a construction just like the Verma module, but it's kind of generalized Verma module. Verma module is you induce from you take the highest weight. So what is Verma module? Is that you take highest weight, take G is equal to T plus M minus plus M plus, right? You take irreducible representation of T, so we call it C lambda, where lambda is a weight. So this is correspond to lambda. Okay, then the Verma module of lambda is just a C lambda tensor with U of T plus, I like to make it as a lowest way module. So therefore I write it in this way. And then you tensor with U of GC. Okay, so this is a Verma module construction. Okay, so basically it's like induced from the Borel. So this is a Borel. Okay, so here you induce from a parabolic. Okay, it's a little bit abstract, but later I will give more explanation. Anyway, the point is that these modules are unitary highly swayed modules. And in fact, later, I think Enright, Hall, Warlock showed that almost all unitary highly swayed modules for these groups. Actually, I think for UPQ star 2N and SP2, I think for these two groups, all unitary highly swayed modules occur in this way, occurred as theta lift of a finite dimensional representation from the compact dual pair. Okay, so you may wonder why I spent so many times for the compact dual pair, because this is the basic things. And all other result for the Archimedean field is related to this compact dual pair. So let's first recall, how do you classify irreducible representations of compact group? over the real field. So for UM, so we classify it by highest weight. Okay, so for this group G, so G is compact reductive group. We basically use unit Wiles unitary trick to show that. So you have G can be put inside a complex group GC, and then irreducible representation of G is in 1-1 correspondence to irreducible algebraic representation of GC. And the irreducible algebraic representation of GC is 1-1 correspondent to the weight in dominant chamber. Okay, so basically you need to know the root system of this group, and then you need to know the dominant chamber, and then each weight will give you so each weight will give you a Verman module like this, and then it will have a unique irreducible quotient, which give you this irreducible representation. Okay, so this is the highest weight theorem in one picture, a highest weight theory. So for UM, so its complexification is GM. Okay, UM is sitting as a subgroup of GM. Okay, so you consider GMC over C. You consider what should I say? You consider the algebraic representation of GMC basically. Okay. So the dominant chamber is given by this kind of inequalities, basically, requirement of these numbers. So the highest weight is parameterized by a chain of integers, decreasing integers. And so irreducible representation of pi m is parameterized by a chain of integers a1 to am, so that a1 is bigger than equal to a2, bigger than equal to a2 is bigger than equal to a3. Okay, so how do you realize this representation concretely? I suggest you can read either House perspective on invariance theorem or Goodman Warlock. Okay, so I will send the paper in the group. And okay, so for irreducible representations of orthogonal group, it is again from the highest weight theory, you basically will have a set of integers a1 to am divided by 2, and but orthogonal group is not connected, so you have to deal with the sign. So this epsilon tells you about the sign. Okay, so but this is not a good classification somehow. For at least for theta. So for theta, we will use this kind of way to define the classification. Is that we all observe that OM is actually a subgroup of UM. So for any weight, any set of weight, lambda, so you will have V lambda, this is the finite dimensional representation of UM, then it will contain the highest weight C lambda. So we will define the representation of ON correspond to lambda to be the representation generated by the highest weight under the OM action. Okay, so you can show that this is actually an irreducible representation if the weight is satisfy the condition below. So if the weight has a form that A1 to AK such that and then you have epsilon from either 0 or 1, and such that if epsilon is 0, then you only require AK is bigger than, you require that AK is bigger than 0. And if epsilon is equal to 1, then you require that AK is bigger than 1. It's kind of weird. Okay, so how do you understand this situation is that instead of thinking about numbers, so you can think irreducible representation of UM is classified by Young diagrams of height at most M. So how do you correspond it? This is A1 bigger than A2 bigger than equal to AM. So this will correspond to a Young diagram with the first row has length A1, second row has length A2, third row has length A3. And so it can be, the row length can be 0. So the last row has a length AM. Okay, so what is this condition? Maybe I should add one more page. So unfortunately and fortunately, the representation of compact group and complex group are combinatorics. Okay, so the irreducible representation of OM is classified by Young diagram of let me see. Right. It is classified by Young diagram of height at most M again, but right, at most M and the length of first two columns, the sum of the sum length of columns is less than or equal to N. Okay, so for example, so the trivial representation is corresponded to trivial representation has highest weight 0, 0, 0, 0, right? And epsilon is 0. So this is just correspond to empty. And the sign representation has k is equal to 0, all epsilons are 1. So this corresponds to this column with length m boxes. And the other generic representation correspond to a diagram like this. So the first column has m1 length, and the second column has n2 length, and you have something else, I don't care, but n1 plus n2 is less than or equal to n. So this is a general case. Okay. Right. And so the correspondence occurrence is dominated by this kind of expression actually. So OM representation occurs in the correspondence if and only if the non-zero entries. Okay, so right. So if you have a tau, which is a sigma, which is a representation of OM, so theta sigma is non-zero, is equivalent to say that this number m minus k is actually smaller than or equal to n. Okay, so recall that G and H is OM and SP to n. So this is the condition. So from this, you see that if your representation is a sign representation, then it occurs exactly. So sigma equal to sign imply that m minus k is equal to n, because k is 0. Oh, sorry. K is right, k is 0. K is here. So your epsilon is non-zero. Epsilon is 1, but k is 0. So this implies that's the first occurrence. Is so 2n. Okay. So this is the latest occurrence possible, right? Because k cannot be even smaller. So the sign representation actually occur latest. So this is a general phenomenon. Right. For SP2M, the representation is again classified by these numbers such that the highest weight is generated by the weight like this. Again, right. Okay, so again, this is, you can view it as classified by, where am I? So you can view this is classified by the Young diagrams. But I think, am I right? Okay, so yes.
So for OM and P2
Yeah.
require M to be equal?
No, it can be odd. Then this will be, it will correspond to metaplatic group. So it will be lowest weight module for the metaplatic group.
So it's odd, then it's MP to M.
Yes, right. Then, okay, so I think let's describe the correspondence. So suppose your representation give you a number like this, a chain of integers where A1 to AK are all positive integers. B1 to BL are all positive integers. K less than equal to P and L less than equal to Q. If I suppose I give you this kind of chain of numbers, then you can consider the irreducible representation with highest weight with this kind of shift, where R, okay, sorry, here should not be RS, but PQ. Okay, so you always need this kind of shift. And then this irreducible representation will correspond to the lowest weight module of UPQ, where this UPQ is the lowest weight module with lowest K type has this form. So this basically it is that you have the chain of A's, you copy this chain of A's here, and you have a chain of B's which are positive numbers, you copy it here. Okay, so but you have to do some shifting. So that's it. I will explain the shifting later from the Fock model, but anyway, you remember you will have some shiftings. And for the orthogonal group is similar. So if you have this kind of numbers represents the irreducible representation of orthogonal group, then pi mu is correspond to the lowest weight module with highest weight mu. But actually with the shifting, which is plus n divided by 2. Okay, so you see that when m is odd, it becomes half integer. So highest weight become half integer. So it's a representation, not on the symplectic group, but a mathematic group. So actually, second case is a consequence. If you have do the computation for 1, then you can deduce that from again a seesaw argument from 1 to get 2. Plus the right, plus explanation before. Okay, so and the third case is when your m when your a is a chain of integers like a1 to ak, and the k is less than equal to the largest number, less than m and n, then the irreducible representation of SPM will in 1 correspond to irreducible lowest weight module with lowest K type mu plus m. Here this m you should understand as 2m divided by 2. So because sp2m its complex form is actually sp2m. Okay. So you always have this half at somewhere. Okay. So that's somehow the point. So theta is kind of a way to take square root of your construction. So I think let's continue so we can finish earlier. So as an application of this compact dual pairs correspondence, we can more or less, if you know the compact dual pair correspondence, plus some very clever argument, you can deduce the small theta correspondence between complex groups. So, but before I explain the result, I should explain the classification of irreducible representation of complex reductive group. So Yeah, so that's why theta correspondence is difficult, is that you have to know all the aspect, or at least a classification result about the irreducible representations of reductive group, and it's not very easy to learn. Okay, so the representation of complex reductive group is what was settled by Selebenko. But how do you get irreducible representations? Okay, nowadays you know that it can deduce from the long length philosophy, or long length realized as long length quotient. But what is the explicit form? So let's recall. So our setting is that let G be a complex connected reductive group, and we take a Borel subgroup of G. Okay. Again, it's a complex Borel subgroup. So its maximal torus inside Borel, which called E, which is Gadang, is actually isomorphic to n copies of C cross, where n is a rank of G. So n is a rank of G. Okay, so but what is C cross? C cross is U1 cross U1 cross R bigger than or equal to 1. So which maps A to its modulus and okay, its angle direction and the modulus direction. Okay, so this is a group homomorphism. So what is the representation of U1? So irreducible representation of U1 is classified by the integers, right? Irreducible representation of R bigger than or equal to 0, sorry. So this is 0. R bigger than or equal to 0 is on the exponential map isomorphic to R as an additive group. Okay, so therefore the irreducible representation R is classified by complex number. So basically the classification is that if I give you a chain of integers, okay, so let me. So what is the irreducible representation of C cross is given by the pair of integer and exponent nu. Okay, so we're in say and okay, so this is just a say cross C cross no C. Okay, so where so I think I should write in this way. Where n nu is mapped to the character which sends say to the modulus to the power n. Say divided by say to power n, and this to the power nu. Okay. So say divided by say is just a unit vector. You can consider the n power of a unit vector. It's again a unit vector. This is well defined. And then for any real positive real number, the power of a complex power of the real number is well defined. Okay, that's how this is a correct definition. So this say to the power of nu is just e to the power of log say to the power of nu. So e to the power of a complex number is well defined. Okay, so in general, you have n components, so you will have n integers and n complex number to classify irreducible representation of the Gadang. Okay, so then we can define something called a standard module, which is that if I give you mu and nu, you consider this character chi mu nu, and you do the normalized parabolic induction, and you get a possibly reducible representation called x mu nu. So this is normalized parabolic induction. So the normalized parabolic induction basically specifies the condition that it sends unitary representation to unitary representation. Okay, so among them, so recall that mu is a compact torus. So this is T. So G has a maximal compact subgroup. So it will contain this compact torus T as its maximal torus. So you will have a finite dimensional representation. So with extreme vector weight, which is mu, or in other way, I can say that G is a representation with of K. Its maximal compact group will have a irreducible representation, has highest weight, is inside the Weyl group W orbit of mu. Okay, so let me call this representation F mu. So in this standard module, there will be a very specific K type, which is called F mu. Actually, you can see that this is a lowest K type, and this occurs with multiplicity 1. What's the definition of lowest K type? Lowest K type is a K type has minimal length, but this length is normalized length. It's due to defined by, it's not the length of mu, but you have to do some shifting. The actual formula is quite complicated. I cannot recall. Okay. But anyway, so it's a minimal length possible mu in the sense of Vogel. Okay, so then a theorem tells you that actually this in the standard module, you will have a unique irreducible subquotient contain this K type F mu. And we call this X bar mu nu. Okay. So the theorem of Selebenko tells you that the irreducible representation of the complex group G is in one corresponding to the W orbit of this mu nu. W orbit of irreducible representation of H. So H is a Cartan subgroup. Cartan subgroup is having so this H is actually the normalizer of H divided by the H, right? Oh, no, sorry, not H. You can think the Weyl group is normalizer of H divided by H. So this Weyl group act on H, so it's also act on the irreducible representation of H. So so the W orbit of irreducible representation of H in this way will give you uniquely give you a irreducible representation of G. So this is a parameterization. Okay, in practice is that so you have say n cross Cn, and your Weyl group, for example, for GLN case is just a permutes the coordinates, just a permutation of the coordinates. And but the coordinates on C and Cn are like a step So you have a Sn action on Zn, you have Sn action on Cn. So the actual action is diagonal Sn action on Zn cross Cn. So this is the while group of the complex group. Okay, so right. So I think I can give an example is that, so irreducible representation of GLNC is in 1 correspond to a chain of Ni and mu I divided by Sn action. Okay. Okay, so this is a classification. But again, if you're doing theta, so you have to face orthogonal group. So what is a class? So the previous classification is that you assume G is connected. So if G is not connected, you have to deal with the non-connectedness. So for orthogonal group, the point is that it will contain special orthogonal group. So instead of thinking mu as irreducible representation of, so mu is purely is like a weight, right? But you think mu as, but it will give you a weight of SOM, which is a maximal complex subgroup of SO and C, but it will, you think mu as irreducible representation of OM, sorry, OM. Okay, so then what you do is, instead of considering standard module for SO, you consider the standard module for O, which is just the induce of the standard module of SO. Actually, by the induction of stage, by stage, you can think it is nothing but the induce of OMC of SOMC of chi mu nu. Here, this mu is again a weight of T actually. T. When you restrict on the Borel, you also think as it's a weight of T. Okay, anyway, so you induce this one and it will contain two K types, mu and mu tensor sign. It's possible that mu and mu tensor sign are the same representation. It's okay. And the point is that you take X bar as irreducible subquotient of the standard module, which contains this specific OM type. The ON type. Okay. So this is the comment for the orthogonal group. Then after that, we can start to right. What we have to do is we still have one ingredient lake, which is the correspondence of infinitesimal character. So do I need to explain what is infinitesimal character? Okay, so I think it's quite important. So let me do it in one page. Okay, so what is the infinitesimal character of a representation of real reductive group? Actually, you should think it as representation of universal enveloping algebra. So what you do is that you have a group, real reductive group G, and then you consider the Lie algebra of G, which is G, and the irreducible representation of G will give you a representation. So it will give you the High-Shander module, which consists of or K finite vectors, where K is your fixed preferred maximal compact subgroup. And then this on the K finite vectors, you will have the algebra action, and this the algebra action of the complexified the algebra of G. So GC is G tensor R over C, and this will introduce a universal enveloping algebra action on the High-Schendel module. Okay, so we can consider an important thing is called annihilator ideal, which is, I think it's correct, which is the set of all element X in the universal enveloping algebra so that pi X map to 0. Okay, so this is an ideal. Ideal in the universal enveloping algebra. If pi is irreducible, then you will know that this will be a something called a primitive ideal. So it's a, I think it's a prime. Okay. So on the other hand, so you will, this universal enveloping algebra will have a center. Let's call it a CG. It will also act on pi, and the Shor's lemma will tells you that the Dix-Mears version of Shor's lemma will tells you that CG act by a scalar. So this means that CG intersect with the annihilator ideal, it actually is a maximal ideal of CG. So this is a maximal ideal. Okay, so we'll say CGC is the center of this one, and okay, so therefore, by High-Schendel, you will actually know that the center, so there's something called High-Schendel isomorphism, will tell you that the center of the UG is actually naturally identified with the symmetric algebra of the Cartan subalgebra and taking the W invariant. So W is a wild group act on the Cartan subalgebra. So as a consequence, it means that the spectrum or maximal spectrum of ZGC is actually some kind of quotient space of H star C divided by W. You can, roughly speaking, think about it's a W orbit on H star. So spec of HC is just the H star C. Oh, no, sorry. Spec of symmetric algebra of HC is just the H star C. Okay. So, but you take the upper W invariant, then it will correspond to taking the quotient of W in the geometric. So I say this is because our essential goal is a relative long length. So you should see this kind of correspondence between algebras and geometric spaces. Okay, so this is, so therefore, as a consequence is that this is a maximal ideal, so it will give you a point inside the spectrum. So this is nothing but a W orbit in the H star C. So infinitesimal character is a W orbit in H star C. Okay, so right. So example is that we have mentioned before, G is a connected complex group. Then UGC is actually, so GC is actually isomorphic to G direct sum with G. Okay, so this isomorphism is non-canonical, but it's isomorphism. So therefore, the universal enveloping algebra is a tensor product of universal enveloping algebra of G with G itself. And the ZGC will be two copies of ZG together. So therefore, the spectrum is just a H star plus H star divided by W cross W. And it's a fact that as a consequence, it's a general fact of the normalized parabolic induction is that parabolic induction preserves the infinitesimal character in the sense that if you have x mu nu, then, okay, I forgot to say that the infinitesimal character of this character of chi mu nu is just half of mu plus nu, half of mu minus nu. Okay, so I'm cheating a little bit, but let's assume this one, and then the normalized induction, it will actually also have, although it's not a irreducible representation in general, but the center still act by scalar, so the scalar is determined by this one. Okay, so anyway, the message is that from x mu nu, you know the infinitesimal character. So in many cases, minimal K-type will determine irreducible representation, but in general, it's not. So these two information will determine the representation. Just infinitesimal character and the minimal K-type. In nice case, for example, this AQ lambda. Okay, you know the infinitesimal character, you know the minimal K-type, then you know the AQ lambda, and also like for the holomorphic. Okay, holomorphic discrete series is even extreme. You know the minimal K-type, you know the infinitesimal character. You can determine the representation. But in general, it's not the case. Actually, yes, last night I asked, I was thinking that this is true, but actually I asked Daniel Wang and he told me that it's not. So the typical example is GL3C. You can have two representation which has the same minimal K-type. So this is the Atlas code which shows that the minimal K-type of, I think one representation is this one. Another representation is, okay, another representation is that you replace this number by this number. And then both of them has the same minimal K-type like this. Right. Okay, so, but, right, what's my point? So infinitesimal character is quite important for theta correspondence is because pi had, so you have a dual pair, G and H, so you have pi, and you have theta pi. So the theorem is that so the infinitesimal character of pi determines infinitesimal character of theta pi. Okay, so this is this is a message, but how do we prove it? And I want to present a quick proof. or at least some hints of the proof. So how do you know there's a correspondence? So this related to something called a Fock model. Recall that the complexification of the algebra of SPW is actually isomorphic to the symmetric algebra. Symmetric, symmetric square of W. Okay. So the Lie algebra is actually of symplectic group is actually isomorphic to symmetric square. So suppose we choose the polarization of the complexification of W as X plus Y. And so we think X as, so you take a basis Xi and take a dual basis Yi. Then let Xi correspond to Xi and Yi correspond to the partial derivative of direction Xi. So these operators will act on the space of polynomials on X. Okay, so we call this PD, which is basically polynomial coefficient differential operators. This is called a Weil algebra. Okay, so somehow the big SPW, so big SPW, so the Lie algebra of big symplectic group. So our assumption is that G and H is a real reductive dual pair inside the SPW. So then the Lie algebra of SPW, then complexified will have cut-down decomposition of compact group part and the non-compact part. And the compact part will have a basis like Eij. Okay, so this K is actually isomorphic to GLN. So if rank, so dimension of W is equal to 2n. So this is GLNC. And so it will have basis like Eij. So then you can right, you can define a little bit confused. I think this is a correct one. So you can map Eij to this operator. So you can check it to satisfy all these break relations. And so the non-compact part will have two parts. So basically you think the algebra of SP as this has a GLC here, GLNC, and then you have a symmetric square here, which is called a P plus, and then you have a symmetric square of X. So symmetric square of X and the symmetric square of Y below. And this is a P minus part. Yeah, I'm sorry, I'm writing so small, but this is a structure. So, but basically P plus part correspond to multiply quadratic polynomial EI, EJ. And the P minus part are taking twice of partial derivative, partial Xi, partial Xj. Okay, so you know that Xi, Xj is equal to Xj, Xi. And the taking partial derivative also commute with each other. So that therefore it's correspond to a symmetric square. Okay, so this Lie algebra action is just by above. So action. Okay. So this give you a full description of the action. In particular, you see that the center of K is actually act by this number, which is the you see the half of n. This is because xi partial xi is equal to partial. I think the canonical commutator relation. So this one is equal to -1, right? you can test for any function. If it's a constant function, multiply xi, then take derivative of xi, so it's 1. All right. So you can x this one by 1, then you check this is 1. X this on the constant function, or a constant function 1. Then the derivative of constant function is 0. So you have this relation. So therefore, the center is actually x by this one. So therefore, you always see this half, because half here. Okay. So the point is that the Weil representation is a universal enveloping algebra of SPC. Under the Weil representation will map to the Weil algebra. And actually it's surjective to the degree 2. So it's a plus minus 1 invariant subspace of the Weil algebra. So it's a simple case of SPW01 dual pair. O1 is just plus minus 1. Okay, in general, okay, so in general, you will have this fact. I should be quick. So this fact is that W, the image of the universal enveloping algebra UGC, is actually the G prime C invariant of the polynomial differential operator. And the image of G prime C is the GC invariant of the polynomial differential operator. Okay, so therefore the center of, say, GC is nothing but UGC and the GC invariant. But this is a algebraic map, so therefore you can take it as GC invariant of the image of universal enveloping algebra. So this is nothing but polynomial differential operator G prime C invariant, then take GC invariant. But this is nothing but polynomial differential operator of GC cross G prime C invariant. So you do the calculation again, so you will see that this is nothing but the image of universal enveloping algebra G prime C. So the message is that this image under the Weil representation, the center of both groups will map to the same algebra. Okay. And it basically says that if you have a map between algebra, then you will have spec B map to spec A, right? Okay, so here is the same. So you have say GC map to this one, and you have say G prime C map to this one. So you will have a map from the from this one to the below spaces, below algebras. But there's one more thing, is that if rank G is less than or equal to rank G prime, actually this omega is an isomorphism. Omega from UG to this PD. G prime C is an isomorphism. Okay, so in this case, you see this is isomorphism. So therefore you have an embedding of the spec, say GC to spec of say G prime C. Okay, so then this one is nothing to do with, everything is actually just complex group. So there's nothing to do with dual pair. And you want to pin down this map, then you can use a compact dual pair result to pin down it. So as a consequence is that if the rank of G is less than or equal to rank of G prime, then what you have is that if W has infinitesimal character lambda, then big theta pi has infinitesimal character lambda prime. where lambda prime is lambda concate with lambda tilde, where lambda tilde is given by these formulas in these three cases. Okay, that's all for today's lecture. Thanks. I think I say too much. Okay, so see you next week. Hopefully next week I can discuss something about the finite field case.